So today we'll discuss about an electric field in continuation of the previous lecture. Okay, so basically, a charge, if this is the charge Q, it produces something called an electric field in the space around it, and this electric field exerts a force on any charge placed in the vicinity of this particular charge. So what we can say is that it's something like this. We can just imagine an imaginary line of forces coming out of a charge, and if we place any another charge in the vicinity of this charge is going to observe the field, some kind of a force acting on it. So what we can say that because of this charge, you'll find that the force that will acting on this Q because of the electric field E. Now suppose if this is an electric field E over here, so you'll find that the force acting on this charge will be F is equal to vector F is equal to E into Q, where E is the electric field, or E can be written as F by Q, or we can say electric field is the force per unit charge. Okay, now what we know is that this field lines, these are the imaginary field lines actually. Okay, and what we know further is that we just assume that this positive, the field line is coming out of this charge, and if there is a negative charge in the vicinity of this charge, you'll find that this will culminate into this charge. Okay, so the important part of this line of electric line of forces is that they do not intersect each other. Okay, they have a unique direction and they never intersect, and they just enter the. So this is what we know. We should have an idea about the electric line of force, or electric field rather. Now this field is directly proportional to the value of the charge over here. Stronger, the greater the charge, stronger will be the field. Okay, so this could be understood in this way, that if you have a charge over here, and what you can say that this is the electric line of forces. If the charge is very small, it will be something like this. Okay, so if you draw a normal line of force, you will find that this is the only line of field line passing through it. If you increase this value of charge, number of line of forces will increase, and you'll find that the number of line of forces passing through this area also increases, thereby increasing the number of field lines passing through this. Means what? That the force acting on a charge placed over here will be more in the latter case than in the previous case. So this is the thing which you'll have to remember. Now what you'll have to do is that we need to find out the relationship between the potential. Now we know what is potential. We have already discussed in the earlier lecture about the potential. So if we have to find out the relation, okay, between E and V. So we need to find the relation between E and V. So how to find the relation between E and V? Now we'll just assume electric field at a point, okay, due to a charge distribution, and let that field be E, okay, and electric field at the same point is V. Let this be the point. Now a point charge Q is displaced slightly from the point. Now what we'll assume that let this be the point, and here, okay, this will be the point. Here we just assume this one to be the point R, and we just displace it to a new position R plus dr. So ultimately this position, this displacement is very small. Okay, so in this particular situation we can assume that the force practically will be same. It won't change. The value dr is very small, very small, so it may not vary. Because of this, the force will not vary. So ultimately what we will say that the force will practically remains the same, and in the process the work done to move the charge from this point to this point will be given by Q into E, or rather sorry, this is the F dot dr, sorry, extremely sorry, F dot dr. Okay, so in the place of F we'll write QE into dr. So we have just assumed a charge over Q over here, and it has been displaced from R to R plus dr. So in the process, this is the work done. Okay. Now the change in potential energy. In the process, the change in potential energy will be given by U is equal to minus dw, okay, which is equal to minus QE dot dr. Okay, so this is what you'll get. So the change in potential energy, further energy and potential, from the energy potential relation we know that du equal to q dv, which we have discussed earlier. So dv will be equal to du by q. Okay, so we'll substitute this value over here. So we'll get minus QE dr by q. So that will give you minus E into dr by dv. Okay, so with the dot product over here, right? Now integrating between the limit, okay, we'll displace the position, we'll displace this charge from R1 to R2. Okay, so in this particular situation what we'll have is like this, dv, okay, say from V1 to V2, okay, and will be given by R1 to, so from here we'll write minus over here, R1 to R2, R1 to R2, and then E dot dr. Okay, so ultimately this will be the relation, and in the place of this you will write V2 minus V1, okay, after integration, and you'll get something like this, minus R1 to R2 E dot dr. So this is what you'll get, and this is the relation between the potential and the field. Okay, now what we can do is that if we'll substitute if we put the relation like this, that we'll do one thing, that we'll consider a particular direction and we'll start R1 will taken to be 0, and if we consider the direction along the distance along x, actually say, so we'll just substitute dx in the place of E, and we'll put d over here. So from 0 to d, and here we'll have say dv, so the change in potential from 0 to d, so you'll get dv. So this is what you'll get. Okay, so ultimately if you integrate this thing, you'll get ed is equal to again v. So this is what relation you'll get. Ultimately the form of the relation which you'll get is like this, dv is equal to minus edr, or E equal to minus dv by dr. So this is along any dimensional space. So if we talk about the component, it will be something like this, Ex is equal to minus del v by del x, or Ey equal to minus del v by del y, or Ez equal to minus del v by del z. So this is a very important relation basically. While solving the numerical, we used to, or rather we very readily use this particular relation to find. Here we just remember that field is it's a vector quantity, so it has a direction obviously, so it's always along the direction of the force. Okay, the field will act, and in the next lecture what we'll do is that we'll discuss about the field due to a dipole. So that will be in the next lecture. Thank you.